Hello and welcome for another lecture for your Earth Science course. This one we'll be talking a little bit about a day at the beach. So we'll be introducing some of the fundamentals of coastline, beaches, as well as waves, and really just the whole process that occurs there. Again, um, this is kind of a shorter presentation. It's only got 13 formal slides. This is a lot of information. In fact, if this interests you, I highly suggest that you look into taking an oceanography course where they get to spend a lot more time diving into, no pun intended, in some of the content that we'll see. So let's start. So what I wanted to start off with is a photo. This is actually from my great-great-aunt's photo collection. This is actually Long Beach, 1932, when people used to be able to drive up on the beaches. As you can see in the background, you've got your oil rigs, and it's a very different landscape than what we see today. So let's start off with this. What is a beach? Well, beaches are the interface between the lithosphere and the hydrosphere, the ocean. It's a meeting point. It's a very unique zone. Beaches do not necessarily have to always be on the ocean. We can certainly have beach ridges on inland seas and very large lakes. But the beach is that interface between water and land. The beaches themselves are usually made of loose particles. Beaches can consist of sand, gravel, shingles, rocks, and cobbles. What's interesting about sand is the word sand actually just defines the grain size. It doesn't actually identify what the specimen is made out of. So we have sand that's made out of diamonds, we have sand that's made out of quartz and feldspars, we have sand that's made out of seashells. So we have quite a diversity. Um, Often viewed as a popular seaside resorts, beaches are dynamically responsive to their environment, a human and actual just induced on their own. So we'll learn that it doesn't take a whole lot to change the entire topography and the interface in which we have along a beachscape. So let's begin here. Let's catch a wave. So what are waves? Well, the ocean is never still. Energy travels through it in a circular motion. What's interesting is that when we think of waves, it's actually, we're not looking at the water moving, we're looking at the energy traveling through the water. Waves are mostly caused by winds because of friction between the wind and the surface. So as the wind is blowing upon the surface of the ocean, it actually transfers, because of friction, the wind into the ocean itself. Now, also due to gravitational pull of the sun and the moon, the Earth also will experience tides, which is another type of energy that is transferred. So there's many different types of waves. The best way to identify them is based off of some of their attributes, which we'll talk about in a moment. But here's some classic photos of some breaking waves. So the anatomy of a wave, let's start with just these two fundamental pieces. You've got wave height and wave length. So the wave height is the vertical distance between the trough, which is the low part of a wave, and the top part. So that's going to be measuring our height. Then the wave length is the distance between crest to crest. So this is important for us to understand as a measurement for those who study in oceanography, because understanding the wave height and wave length tells us a lot about the energy that's being transferred within the ocean. So the larger the wave height, then we see that the stronger or the greater the energy. The way that I've always thought of this is that by using a slinky. Remember those little toys that we would use? So if you have a slinky that's very far apart and you kind of just a little bit of energy is needed for it to move. So you don't have a very high wave height or wavelength, but if you move the slinky close together with a little bit of energy, then it starts getting all crazy. So you have a very short wavelength but a greater wave height. We can talk about the energy that's being distributed there. So just to kind of put it in perspective. There's other things that we can look at here within this diagram, but we'll kind of see this a little bit later. But again, this is more the anatomy aspect. So when you're out on a boat, out in the ocean, and you're feeling that that motion going up and down, you're going upon those crests and then down into the troughs back and forth. So moving into the three types of waves that there's actually four, but we'll stick with these for now. We've got spilling, plunging, and surging. So these are the three different types of waves that we can see. What's interesting about this is the first part is the main difference between all three of these is looking at the gradient. So we can see that the beach is very flat, so it's a spilling breaker. The beach is usually steep, so it plunges. the beach is very steep, so it surges. So the name of each one really identifies how it acts on the shore. So when I think of, spilling breakers, it's very flat. It just kind of slushes up and slushes back down. It spills like a glass of water spills over. Plunging, we start to see that there's a greater crest that develops. Excuse me. So we can see that because the slope begins to be increased. When I think of plunging, maybe you've ever were running and you were running on a flat surface and all of a sudden the gradient changed and kind of caught you off guard and then you end up breaking and falling. Think of that type of attribute. And then surging is the type. When I think of surging, it really pulls out, crashes in and then pulls back out like a surge, like an electrical surge where it kind of jolts back and forth. So it's so steep that it crashes very early on, splashes up, and then has a lot of energy pulling it back in. So we have spilling, plunging, and surging. The biggest difference amongst all of these that we identify is the beach slope. You're looking at how steep it is. Now, I guess the bigger question is, well, how does this change? Well, the slope of the beach will change based on sediment supply as well as the season. We actually see that there's a seasonal change that causes our beaches to change their slope. So that's why during the winter we usually see more plunging and surging waves, and then during the summer we see more spilling waves, and we'll talk about that in a little bit. So we've already mentioned, let's go into tides. So what are tides? Tides are very different from waves. They're still in that same family because it deals with how energy is distributed in the oceans. But tides are the alternating rising and falling of the sea due to gravitational pull of the moon and the sun. So what does that mean? Well, we'll start with the moon. So the moon, because it's stuck within our orbit, because of gravity, actually pulls the hydrosphere, the oceans, out a little bit. Now, this has been exaggerated clearly, but this is the idea. So the moon is here. In this case, the sun would be somewhere over by my face. So you can see this bulge has been created. This would be what we consider a high tide. These areas in which the water is very high, versus down here, see how it's been diminished, it's been depleted. These are areas of low tide. So what does that mean? Well, you've been to the beach. You've noticed that about lunchtime, you start experiencing a higher tide, meaning that the waves start moving closer towards where you were building your sandcastle. Well, that's because, now if I hit play here, it should work. Again, not in scale. But see, notice how in this particular image here, there's North America rotating around. High tide, low tide, high tide, low tide, high. You kind of get that vision. Well, because that's what happens in a day. So we rotate one time in a day like this, dealing with the fact that we could get 2 high tides and 2 low tides every day. Now, what's interesting about this is that this bulge, this high tide on either side, is caused by the moon. Well, that's because the moon is in this position here. Well, it takes the moon about 28 days to orbit all the way around the Earth. So, it starts to work its way around. Well, that ends up changing the tides. That's why the tides aren't always the same. In fact, that's why if you're a surfer, you notice that you have to listen to the tide report to see, well, what is expected today? What is the correlation with where we are in relation to where the moon is and what phase the moon is? So we're looking at a new moon. Are we looking at a first quarter, second quarter, third quarter? That really changes the tides, which is kind of interesting. Now, I'm going to stop that there. Again, that's the moon. Well, what about the sun? Well, the sun only pulls about half as hard because it's about 400 times farther away, but it's still an incredibly large mass that does have a pull. So as we can see in this diagram here, what we have now is when the moon is aligned here, we have extremely, or otherwise known as super high tides, and then we have super low tides. Super high and super low tides occur when the moon and the sun are either next to each other or the moon is on the opposite side still aligned. Well, what's a good example of a super low tide? Well, maybe super low tides, there's, of course I can't think of it off the top of my head, there's a coastal city in California that when we get super low tides, the water is so far out that you can actually walk out to a sunken ship that's in the harbor there. So when we see those examples of extreme amounts of water being pulled away from the shoreline, it's because it's being distributed to somewhere else. Again, simplistically, that's what tides are. They're a lot more complex. There's some additional videos that I've provided in the modules to help with trying to understand a little more if you're interested. But again, it's pretty fun. If you're taking a lab class, you'll do an activity that deals with Don't make fun. I did a little diagram like this. I call this, it's part of the tide-o-matic. I took this from an organization, it's called NOAA, NOAA. But anyway, so what we have here is you have the sun, you have the moon, and then you have the little earth right there. And so what we can do is, based on, we'll zoom in, this bulge that goes around here, that big bulge represents the high tide. So when I go ahead and I grab this and I rotate the moon to a different spot, you see how the tide starts to change? And then there's a little one here for the sun. So when I start spinning the sun, you can see the little yellow bulge is moving here. So anyway, there's a whole video that I posted on YouTube that kind of explains the tidal-matic, but that might be another way to try to interpret it. So here's another example of what that looks like. So we can see again where we have new moons and full moons and what this really looks like. So again, I just saw this image. I thought it might be helpful for other people to envision. So I'll give you guys a moment to go ahead and check that out. So this just really takes you between the new moon and a full moon. So the new moon is when the moon is closest to the monthly orbit, or the perigee, and then you have when the full moon, which is the moon is closest in the Earth in the monthly orbit, again on then the other side. So, all right, so I'm gonna move on. You can always pause the video, right? So another way that water moves, we'll talk about the current, so the current event. So oceanic currents describe the movement of water. So I broke this into three parts. So you have the rise and fall of tides, you have winds, and then you have the thermohaline circulation. So the rise and fall of the tides themselves can create a current within the ocean, which are the strongest near the shore, such as riptides. They're called tidal currents. So currents are these very, very large, it's like part to whole. So taking these smaller pieces of tides and smaller pieces of waves and looking at the grander scale and where it really works in a more continental or than global landscape. Another thing looking at is winds. Well, winds drive currents that are near the ocean surface. Near coastal areas, winds tend to drive currents on a localized scale and can result in a phenomena such as coastal upwelling, which is really that circulation motion that can occur. And then the thermohaline circulation, which is probably the one that you're most familiar with. This is the process that's driven by density differences in water due to temperature and salinity. So we know that colder, saltier water is more dense, and so it sinks. So this little diagram I put on the presentation here shows a bunch of the different types of currents. So we have the Antarctic circumpolar drift that moves water going this way. It slowly, as you can see, mixes within this, by Brazil, and then it starts, it warms up, and then it starts, because it mixes, it cools down, and so we have all these different cycles. Am I asking you to memorize all the currents? No, that would be for an oceanography course. What I'm asking you to identify is, okay, I see that there are correlations with water. I can see that within the tropical zones that water is much warmer. I see that in Arctic areas that the water is much cooler. I see that there's a mixing, very similar to how air mixes. I also want you to understand, very simplistically, that because of this cycle, if you change the temperature or the salinity, the circulation will also change or adapt. So there's a lot of really interesting conferences about the facts that that we have climate change occurring, right? And that we see additional amounts of ice are melting and going into the oceans. Well, by adding warmer water to the oceans, we'll change the temperature. By adding additional water to the oceans, we'll change the salinity, right? You add more water, it becomes less salty. And so there's been a lot of projected models that will say that if we get to a point that we add too much water to the oceans, that it will not be salty or cold enough to circulate. And in fact, these currents will actually cease to exist. They will stop operating. And if that were to occur, then the areas in the middle will stay warm, and the areas on the outer edge will stay very, very cold. In fact, it could induce what's identified as a snowball Earth, which means it would freeze from poles inward. So again, interesting stuff. So I mentioned a little bit about seasons. So here's a couple diagrams, so the anatomy of coastal environments. So looking here, we have a summer beach and a winter beach. So what's interesting is that during a summer beach, we find that the waters during summer, the waves themselves the energy is not as great. That they crash, they're very slow, low energy, which actually slowly pushes sand up onto the beach face. We find that during the winter that the waves are a lot more aggressive, a lot more energy. So when they crash, they actually pull sand away from the beach face. Sorry, my nose itches. It's this light. So what we can see is, well, why does that occur? Well, we find that most of our larger storms out in the oceans occur during our winter season. So then, since you have bigger storms, you'll have bigger energy displacement, bigger waves, which will then carve away more of your beach face. What's interesting though is that this berm, this sand berm, is developed here. It actually just gets relocated farther out. So maybe you've been to a different beach in a different location in the world. When I went to Cancun, I know, I'm fancy. You'll notice that because they get a lot of smaller waves throughout most of the year, you walk very, 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 very far out, and you're still maybe only down to your knee, maybe your hip. But then maybe you've been to places in California where we get different types, get more storm surges, or maybe even on the East Coast, where you don't walk very far out, and all of a sudden it drops off. Maybe that'll help. Again, if you're a surfer, you understand the difference. You understand that, yeah, summer waves are not as cool to surf on because they're low energy. Winter waves are better to surf on, but they're a lot more dangerous. Another thing that's interesting about this is that if this occurs, so you're taking from sand here and removing it, you might be thinking, why is there sand at the beach all year round, such as maybe in Ventura? Well, that's because we actually put it there. We'll learn a little bit about this in a moment, but sand will actually move. It doesn't really necessarily move on and off. It moves at an angle. And sand slowly moves down the beach face, going downwards. So in our case, it goes down south. Well, if you have these larger waves, all the sand will be deprived, which means it'll be gone. And if you don't have another resource for sand, your sands turn into rock or whatever's underneath this area, this berm erosion. Well, we don't want that for tourism, so we actually dredge it. It's very much like a nunu from Teletubbies, and it's like a big straw, and it sucks up sand and takes it into the ocean, up in a tube, and dumps it back farther north so it can recirculate. So we always have sand on our beaches. So it's actually, we have artificial beaches in most of California. So this is a beach system. This is a very complex diagram. So I'm not asking you to stress about it quite yet, but we can see that we have these different elements of what occurs. So you have, the dune, which is that big berm. So this is where you walk up to the beach, and then you go, then you go down, and then this is where you put your little your umbrella, and your family hangs out, and then you mostly hang out down here somewhere and build your sandcastles and deal with the tides. So we can see that we've got the beach zone. This is where the surf crashes. That's the surf zone. And then way out here, 1 to 2 kilometers, that's the actual continental shelf. That's the edge of the continent itself. So let's look at this real quick. So these coastal landforms, I found this diagram. I thought this was kind of fun. So landforms completed, through the process of erosion, transportation, deposition. You'll hear those 3 words a lot throughout the rest of this semester. So what I have here is this really interesting diagram. So you see there's rivers and streams that are adding water to our oceans and to our beaches. Well, they're not just adding water, they're adding sediment or material. And why is that important? Well, that's where our sand comes from for our beaches. So if you build a dam, it actually restricts the material that's going to be going into the beach. So if all the rivers were to no longer go to the ocean, we would have no sand on the beach. You'd have no origin of sand. So it's very important. You also see this little arrow. This is what we call sand transport. It's called the longshore current. So what ends up happening is once the sand gets on the beach, the waves crash and slowly move the sand downward, down the beach. So think about it. You've gone to the beach, your family's sitting out there, you're going in the water, you're not doing anything, you're just sitting in the water in your little raft. And the next thing you know, your parents start looking down, you're way down the coast, you're heading down towards San Diego. And they're like, what are you doing? You got to get out of the water, go back up the beach and get back in the ocean because you're in that longshore current. As the waters come in at an angle and come back out at an angle, they're slowly actually taking you down the beach face. Well, sand does the same thing. So if I hit play here, oops, there it goes. So, slow diagram. But what's interesting is you can see the sand comes down, the longshore current at an angle brings it. So because the sand slowly moves. See how they built this? This is a concrete ridge that they've built here to create a harbor so we can park our boats. Well, because the beach ends, the sand moves down and gets deposited on the end and makes a small hook. Well, that's called a sand spit. If you want to see a really good sand spit, go to Google Earth and type in Santa Barbara Harbor. They have a big spit there. They've got a big nunu. It's called a dredge. And what they do is they suck the sand out of here and they move it over here. Otherwise, slowly, this sand spit would turn into a bar and seal off the harbor. So they have to dredge it. Sand moves down. You see this guy right here. You've probably seen these before. This is stacked rock. This is called a jetty. It's man-made. They do that because what it does is it breaks up the energy of the waves coming in and makes this area a lot more calm. So this is more appropriate for if you have children and you want to go hang out at the beach. You would stay here because you have less likely to have something like a tide that would bring people out and make it more dangerous nonetheless. Here we have a submarine canyon. Those are really neat. So this is what ends up happening is this is a great area for sand to get lost. So sand comes down here, gets caught in a submarine canyon, travels all the way out deep into perhaps even into the continental margin, and then it's gone. So we lose that sand. So we have lots of these submarine canyons. This is essentially an animation expressing, well, where does sand go? There's a great movie. It's shared on online. It's called The Beach, A River of Sand. It's from like 1965. They essentially teach all of this, but what they do is they've created models and small wave tanks, so you can actually see it happen with a time-lapse camera. It's pretty impressive. So anyway, this is an example of that. Oops, there we go. Moving forward, here's some additional landforms. So here is this is that spits that develop that will slowly seal off. So in this case, the water is going from the left to the right. We have this island. We have an island, right? And you have the sand that is developed, so you can walk out to the island. We call this a tombolo. When I think of the word tombolo, it looks like a letter T, kind of. Like here, it sticks out here and makes a T. We can see that these are spits within these bays. If this bay gets sealed off, it'll turn into a lagoon. This barrier island is essentially sand that's slowly. It would have been a barrier bar, if it seals off completely. But in this case, it's almost sealed off completely. It's just a little bit that remains on either side. This is an example of a very, very large spit. So it's that big curve. So you can see that because of the landscape here, it's trying to seal off this area by bringing in all this additional sand. Here's some other coastal landscapes. So here we can see blowholes are very common in Mexico. Where the waves crash and it's like plumbing, and the water shoots through and sprays out the top. But you can see at some point you may get a cave. At some point that cave may be completely undercut and create an archway. At some point this archway becomes so large that it collapses, therefore leaving a stack. And then sometimes that stack will slowly fall over, like these stacks did over here, and they turn into a stump. So again, lots of different features. Definitely take an opportunity to Google some more of these and to be familiar with what they are and how they're formed. So what does that mean? Well, let's test your knowledge. So what I have for you next is, this is a photo I took of the beach. What I have next for you is a diagram, and you should be very comfortable trying to figure out what each of these features are. So what I have, I've left some that are on here. So I've got some bars here. We can see the high tide water, the low tide water. Here's some additional bars in which sand's been pulled off by the water. Here we have some beach berms that are on the beach face, and then you have your dune. So anyway, the vacant answers are A, B, C, D. You have then H is this space here, I is this space here, this point is E, this point is F, and then here's K. Here's all your options. So I would be familiar in your case where the breaker zone is, the shoreline, the near shore, the coast, the offshore, the beach, the coastline, the back shore, and the foreshore. So all of these answers belong out here, okay? So that's where I'm going to leave you on this. So I would make sure that you just go ahead. If you're taking one of my lab classes, you're going to do this exact same diagram and do this as part of your assignment. But I just wanted to share it with my lecturers as well, so that you get a chance to maybe kind of look into it a little bit more. So you should be able to distinguish where the breaker zone is, where the shoreline should be, where's the coast. When I think of the coast, that's where we drive, right along the beach. The beach is where you sit in the sand, right? So start thinking of those analogies or those metaphors to help you understand this environment. All right, well, that's what I have for you for this presentation. I hope you enjoy it, and we'll talk soon.